This is Honors Geometry over sections 5.3 and 5.4 dealing with triangle inequality theorems. And first we're going to look at inequalities in one triangle. If you recall, we have an exterior angle theorem such that when we have these four angles, the measure of angle 1 plus measure of angle 2 plus measure of angle 3 equals 180. Measure of 4 plus measure of 3 is going to end up equaling to 180. So 4 is equal to 1 plus 2. The measure of this exterior angle is equal to the sum of the two remote interior angles. If we take that further, what that also must mean then is that angle 4 is bigger individually than either angle 1 or angle 2. We call that our exterior angle inequality. An exterior angle of a triangle is equal to either one of those remote two interior angles. Next, I have three different parts here. First one I'm saying, to construct a triangle with sides of length 4, 7, and 10. So if I drew my 10 to be this long, and I'm trying to draw it to scale, the 4 might be about that long, 7 could be that long. That triangle is going to be possible. Whereas for the next case, we have 6, 8, and 14. So if this is my length of 14, in order to get the 6 and the 8 to actually meet, they would have to go right along that segment, just like this. In other words, all those segments would have to be in a straight line with each other. All these points are collinear, so that doesn't actually make a triangle. And if we look at this last scenario, 3, 6, and 11, if this is the length of 11, 3 might look like this, 6 might look like that. They wouldn't even be able to reach. They don't make a triangle. So what I would say is that the sum of two sides of a triangle is greater than the third side. Always have to be true. They can't be equal to the third side. Whichever two sides you pick, and normally we're going to pick the two smallest sides just for the sake of comparison, added them together, they're going to have to be bigger than that third side all by itself. Next, we've got a little bit of algebra review. If you took the absolute value of 3 minus 5, you would be having this equal to 2. Absolute value of 5 minus 3 is equal to 2 as well, so those are going to be equal to each other. The example below, it really is exactly the same. When you're subtracting two values and taking the absolute value of them, they're always going to be equal to each other. So that's an important fact for us to remember as we go forward. We have triangle inequality theorems within one triangle. There's two parts to this. Number one, the sum of two sides of a triangle is greater than the third side. That's something we mentioned just before. And the other one is that the largest side in the triangle is opposite the largest angle in the triangle. Likewise, the smallest side is opposite the smallest angle. All those things are going to be consistent when we're looking at any individual triangle. So using that, we are going to try to figure out greater than or less than these problems. As I look in this triangle at the left, there's 152 degrees used up. So if we take 180 minus that 152, we get that the remaining angle would be 28 degrees. So in this triangle over here, the 120 degrees is the biggest. The next would be the segment MY, and the smallest would be segment YE. So if I look in this example, segment MY compared to segment EY, well, MY is bigger. Next, we can move into the triangle here in the middle. We have 113 degrees. It forms a linear pair with the one right next to it, which means they add up to 180, so that angle is 67 degrees. If you add the 67 plus the 48 together, you get 115. So take 180 minus that answer, and this angle is 65 degrees. So now as we look at this triangle in the middle, we know that the largest side is this segment over here. Smaller than that would be segment MC. Let's use a little different marks, so 3 is bigger than 2. And the smallest would be this little one over here. So when we're comparing segment MC to segment ME, ME is larger. Going into our last triangle, this one over here on the right, we know that we have 113 degrees and 17 degrees added together, that's 130. So this remaining angle is 50 degrees. And if we're looking in this triangle by itself, the largest side is this one. The next largest side is this segment over here, and the smallest one is the one opposite the 70 degrees, or this little one on the side. I don't have great markings for these. The 4 is the biggest, the next largest is the circle, and then the triangle. So I'm comparing segment CE to VE. VE is obviously larger. And the last one, comparing segments CM to CE. In that diagram, well, CM is greater than CE because this is opposite the 65 degrees, whereas that one's only opposite the 48 degrees. All right, next one, similar kind of example. We're going to look at this triangle on the left. So far, we've used up 50 and 45 degrees. So add those together and subtract from 180, and that means that this angle is 85 degrees. If we go to the triangle on the right, there's a 140 and a 30 degrees. That's 170. Subtract that away from 180, and that means that there's 10 degrees left for this one. So this is going to be the largest side in this triangle. The next largest side is right here, because it's opposite 30 degrees, and the smallest in this triangle is one opposite 10 degrees segment CR. Now as we go into the other triangle, the nice thing is that this segment CR is the largest side over there. So since it's the smallest for the one on the right and the largest for the one on the left, that means that this segment is bigger than this one, it's bigger than this one, and so we have a direct relationship. If it's in ascending order, we go from smallest to largest, so CH is less than HR, which is less than CR. Those are all smaller than CR, and CR was also smaller than RS, which was smaller than CS. Okay, next type of example. Two sides of a triangle are given. We want to find the range of values for T, which is what we're going to call the third side of the triangle. So we don't know if the third side is the largest side, if it's the medium-sized one, or if it's the smallest one. But what we do know is that if it is the largest, it couldn't have a length of, say, 50. It would have to be less than 8 plus 12, or it would have to be less than 20. And if it was the smallest one, it would have to be bigger than 12 minus 8, or 4. If it was smaller than that, then say 3 plus 8 wouldn't be bigger than 12. So upper bound, we add those numbers together, and for our lower bound, we subtract those numbers. Moving over to the right, 2 plus 6 is 8, and then 2 minus 6 is negative 4. That doesn't make sense, but 6 minus 2 is 4. So we know that this third side couldn't be the smallest side, but it has to be somewhere between 4 and 8. It could be the largest, or it could be the medium-sized one, but those are the range of values. This changes once we put a variable in here. Still, for our upper bound, it has to be less than the quantity x plus 3, but for our lower bound, we're going to subtract those. It's going to be x minus 3, or it's going to be 3 minus x. The thing is, we don't know if x is going to be larger than 3 or less than 3. If x is greater than 3, then x minus 3 is a positive number. If x is less than 3, then x minus 3 would be a negative number. So to ensure that this is a positive value, we're going to put absolute value bars around it, and there is our range of values for t, the third side of the triangle. So for the next one, we're going to add those values together again. We get 2x plus 10. And then for the lower one, because x is the same, and because these have the same coefficient on them, x plus 8 has to be bigger than x plus 2. So we're going to subtract the bigger one minus the smaller one. That gives us a lower bound of 6. Here's our next few examples. Add those together for our upper bound. That's 3x plus 10. Just like we were doing with the number examples, we add those two sides together, and our third side has to be less than their sum. And if we subtract them, we have 2x plus 1 minus the quantity x plus 9. 2x minus x is x. 1 minus 9 is negative 8. And we have to put absolute value bars around it. Because if we did it the other way, if we took x plus 9 minus the quantity 2x plus 1, we would have gotten a different sum here, or different difference. It would have been 8 minus x. But the absolute value of x minus 8 is the same thing as the value of 8 minus x. So either one of those could have been our lower bound. Next one, if we add those together, we get an upper bound of 5x plus 2. So we can just add them together. And for our lower bound, we're going to subtract. Now, depending on the x value, sometimes 3x minus 6 would be bigger. Or sometimes 2x plus 8 is going to be bigger. So we're not really sure which one of those is going to be larger, so we have to subtract them and consider the fact that we don't know which one of those terms is bigger. 2x minus 3x is negative x. 8 minus negative 6 is 14. So absolute value bars for our lower bound. Absolute value bars anytime we don't know which one of the terms is bigger when we're subtracting them. Because if I had taken 3x minus 6 minus the 2x plus 8, it would have been x minus 14 for the lower bound, but this is exactly the same thing. Okay, a variation on the previous problems is not to find the value of the third side of the triangle, but given three sides, could you sometimes, always, or never form a triangle with those lengths? As I look at these, I have three numbers. It's clear that 11 is the largest, and if I check, is 3 plus 5 greater than 11? Well, no, it's not, so this could never make a triangle. Next we have 5, 8, and 4. 8 is clearly the largest, so we're checking, is 5 plus 4 greater than 8? Yes, it is, so you could always form a triangle. Never for that one. Okay, the one on to the right. Here's where we start getting into variables. It's not clear which one of these is the largest. Now 9 is bigger than 4, but we don't know how x compares. So we're going to do two cases. The first case is, what if 9 is the largest side? Well, then 4 plus x would have to be greater than 9. Subtract 4 from both sides, we get x equals 5. The other case is, what if x is the largest side? Then 4 plus 9 would have to be greater than x, or 13 is greater than x. Now we have to interpret these results. Our answer is going to be, sometimes we can form a triangle when x is less than 13 but greater than 5. And if you think about plugging some values in, if x equals 6, yes, we could form a triangle because 4 plus 6 is greater than 9. Or if we plug 12 in for x, yes, it forms a triangle because 4 plus 9 is greater than 12. But if I pick a number that's not in that range, even including the 5 and the 13, it wouldn't make a triangle because one of the sides would be too much bigger than the other ones. Getting into more variable problems, we're going to have cases in this one as well. Because we have those variables in there, it's unclear which is going to be the largest. So let's start with saying 16. If we had 12 plus x plus 2, is that greater than 16 if 16 is the largest side? So we'd have x plus 14 is greater than 16. Subtract 14 from both sides, we're saying x is greater than 2. Case number 2, x plus 2 could be the largest. So when is 12 plus 16 greater than x plus 2? Start working through this one, subtract 2 from both sides. It works when x is less than 26. So our answer to this one is, sometimes when x is less than 26 but greater than 2. We'll do one more here. We have three variables this time, but as I analyze these, x plus 6 is always going to be greater than x. They have the same coefficient on x, but this second one is always going to be 6 larger than the first one. We don't know which is going to be bigger between 2x and x plus 6, because depending on the value of x, sometimes this one is bigger. If I plug in x equals 1, this is 7, that's only 2. If I plug in a bigger value of x like 20, this comes out to 26, this comes out to 40. So we are going to have two cases this time. What if x plus 6 is the biggest? So we're going to take x plus 2x. When is that greater than x plus 6? 3x greater than x plus 6. Subtract x from both sides. Divide by 2. We get x greater than 3. Case number 2. Well, what if 2x is the largest? So we're going to add these two sides together and ask, when is that greater than 2x? 2x plus 6 greater than 2x. Subtract 2x from both sides, and we get 6 greater than 0. So what that means to us is, if 2x is the largest side, it's always going to make a triangle. So our answer this time is going to be, sometimes when x is greater than 3. As long as x is greater than 3, it's going to make a triangle. We can check that. Let's try something that doesn't have an x value greater than 3, like 1. If x is 1, this length is 1, this length is 7, this length is 2. Well, 1 plus 2 is not greater than 7. We didn't expect it to make a triangle, and it doesn't.